Yeah, so welcome back everyone. This is the final talk of this 6-day long course. And the final talk will be given by Dr. Ilan Ziralatan, and it is based on electrical treeing. It is actually electrical treeing under power frequency and high frequency stresses. So, hi Dr. Ilan sir. Welcome to the course. And so Dr. Elan obtained his master's in high voltage engineering in IISc Bangalore in the year 2000 and PhD from IIT Kanpur in 2010. He has published over 25 research articles in various journals and conferences. His research interest includes insulation diagnostics, composite insulation, high frequency breakdown stress studies, etc. Currently, he is a professor of electrical engineering in Pondicherry Engineering College, Puducherry. So welcome, sir, and you can take over for the talk.
Thank you. At the outset, I'm really sorry for the delay with these technical issues. Let me just begin my talk. This is on electric treeing.
Sir, could you go full screen?
Yeah. It's fine now?
Yes.
Am I audible?
Yes.
Okay. The contents is, besides introduction, treeing in AC fields, treeing in DC fields, treeing in high frequency AC fields, and treeing in nanocomposites. I thought to just give an importance of these 4 areas. Some of the introduction we have been hearing from various speakers. Polymers are no doubt one of the best and most economical insulating material because of all these inherent advantages. It can exhibit a high breakdown strength, typically of the order of 10 power 9 volts per meter, low dielectric losses, high DC resistance in the order of 10 to the power 16 ohm meter, high range of mechanical strength and stiffness, high corrosion resistance, and ease of manufacturing, and so on. And due to these inherent properties, it led to the development of synthetic polymer system as well in 1930s. Water treating. I thought I'll spend only one slide on this. Polyethylene was hydrophobic, and so was a choice for power cables in the early 1960s, but failed in few years of service due to water treating. This actually brought an awareness to the researchers that under electrical stress, the material go through a complex phenomena, both physical, electrical, and chemical interactions. And this actually had introduced a triple extrusion techniques, which is primarily to prevent the moisture ingress and also to improve the better dielectric electrode interference, or interface. Because the water treating was it was found to be formed at this interface. Also to use this also had developed cross-linked polyethylene the phenomena in order to manufacture power cables. This had considerably reduced the water treating issues. Origin of tree, there can be void inclusions. Even with the high manufacturing techniques, there are still void inclusions present, and there are protrusions in the manufactured cables and the insulation. They all would cause a local electrical stress, and hence that would be a starting point of the tree. Electrical treeing is it starts from those internal asperities like voids, protrusions, etc. This is followed by a formation of a filamentary pattern of channels, which actually originates from the void, which I'll be discussing in the next few slides. These patterns would be in the form of tree channels. This would be penetrating into the polymer. This defect can act as an electrical tree and grows due to the repetitive discharges. In the tree, this leads to the breakdown process. In the treeing, there could be enormous amount of discharges takes place, depends upon the field condition, depends upon the nature of material. So this intense partial discharge activity in the tree tubules would accelerate the tree channels, would increase the diameter of the tree channels, and would increase the tree structure as such. And finally, the tree structure would reach the ground electrode and would cause a catastrophic failure. In a very thin film polymer specimens at short times, the breakdown field will be in the order of 10 power 9 volts per meter. However, there are many physical and chemical aging takes place in the absence of electrical field. Those chemical changes could be in the bond scission might take place, and the physical structure such as crystallinity also will be altered under the influence of electric field, or even without the influence of electric field, these both can take place. Now, in the presence of electric fields would accelerate those degradation mechanism. Polymers have more voids. They occur naturally in the amorphous regions due to strains induced during the crystallization process. In fact, there were reports that during the manufacturing, it is actually the gaseous environment, and hence the gas formation or the voids forming inside is very much possible. Okay, so though the voids are very small, some cavities may be large enough to support partial discharges at a much higher field of about 10 power 7 volts per meter for 100 micron. Large cavities may also be formed as a result of a cross-linking procedure. So one of the issues with the cross-linking is that void formation is very prone during this cross-linking way of manufacturing. Additionally, other voids may be unintentionally introduced. Yes, initially when the insulation is stressed, which may be even void-free, but under the influence of electric stress, combined with the physical and chemical and other stresses, we will find the voids actually are also formed. Under the service condition and uniform fields, electric trees do not form immediately. But however, when there are protrusions, the voids, the fine projections from the conductor, they are unavoidable. Treeing is none other than the branched, hollow, gas-filled tubular structures, which will have a tree-like aspect. This is one such a situation of a rod electrode from where the trees actually have begun. Electrical trees may be generated at even a low voltage of about 3 kV, but the field need to be high, which should be greater than about 3 into 10 to the power 8 volts per meter at the metallic protrusions. Electrical trees consist of connected channels, as you can see from those figures, and some of the research outputs that you would have seen, you could have very easily observed it, that they are none other than the hollow tubules, but they obviously the presence of the electrons, presence of the charged particles cannot be avoided. They would actually give rise to further enhancement, forming ionization process and so on. So they are actually few microns in diameter with branches tens of microns long. The walls of the channels are partially carbonized. In fact, they are weakly conducting. That is one of the important reasons why even after the tree branches reaches the other end, the breakdown doesn't happen immediately. However, there are there are research reports that has come out in the last more than a decade, which started exploring about the conductivity of the tree channels, which had shown that the trees, particularly in the AC, are mostly conducting in type. However, in the DC, it takes time. It's not that easily becoming conductive. This is the various stages of degradation of the insulation. At time t equal to 0, that is a virgin insulation without any initial defects. But under the influence of electric field, combining with physical, chemical, mechanical stresses, the micro void forms. This is the case with uniform field configurations. Even in that case, the formation of micro void is very much possible. And this void grows. Obviously, in the micro void, there are charged particles. The ionization takes place, and this rises to a bigger void. And in fact, only at the last stage, I have mentioned it as a PD appears. The reason is definitely the void cannot grow from micro void to the bigger void without the PD. Definitely, there is a PD that will be taking place. The only thing is that it might not be at the detectable level. This could be less than 2 PC or whatever, but only beyond 2 PC we are able to detect it and then measure it by using a PD detector. So it will be taking place, but however, after the bigger void forms, the PD starts. Yeah, this picture would be all the more clear how the void is forming into a tree, or how the tree originates from the void. One sec. Yeah. In the first block, here, there are charge particles. They accelerate in the direction of the field. As they the conduction electrons, as they accelerate in the field, they encounter a void. The second picture, a conduction electron encounters the void. As it encounters, obviously, they enter into the void interface because of different energy level. And this electron gets accelerated further in the direction of the field as it gains energy. And obviously, when it goes, it meets or collides with the atom of the gas that is present in the void, forming ionization. And this actually brings forth a more number of electrons and positive ions. So the electron avalanche develops that changes enhances the field inside the void. So and hence the short circuit takes place, or in other words, the partial discharge takes place. And once a partial discharge takes place, it bridges the gap between something like this. It bridges the gap here. The potential difference between this end of the void and this end of the void becomes 0, and hence the void the discharge quenches by itself. And when the voltage goes up, this process repeats. So it is a repetitive process. In the process, as it's mentioned here, this continuous impact of the discharge here, which damages the void walls by carbonizing it, and this process further carbonizes and it leads to a first tree branch. This is how the first tree branch forms from the void, assisted by the partial discharge phenomenon. So once the first branch forms from the void, it leads to many more branches. In fact, those branches which will be conducting, which may be non-conducting also. When it is conducting channels, then at the tip of that particular branch which is conducting will act like an electrode because of its conducting nature, and that leads to further accumulating or further injecting the charges surrounding the dielectric, and that leads to more and more channels, and finally the tree branches reaches the opposite electrode and the breakdown is triggered. This might take even as long as 30 years as per the reports. But that was the case. This was the situation when the plane electrode was in the situation of a plane electrode. However, if there is a rod plane electrode or if it is a point plane electrode, then what takes place here is at the tip here, this region, it is a highly divergent field, and this high divergent field will the temperature gets increased at the high divergent field as the electron gets impinged. It gets accumulated at the tip constantly, and this electron impinging here would begin to break the polymer chain, which means a chemical degradation takes place in the first place. So the CH bond will be broken, and if as the time goes, this continuous process will lead to many more bonds breaking, and that there will form a micro void. And once the micro void forms, that gives rise to the discharges, and further it is something similar to what I've explained in the previous 2-3 slides will be taking place. So that will lead to actually more and more branches. In fact, this this void, that micro void that is started here, that would just gives rise to a small tubule, and the partial discharge would take place in the small tubule, and this would give rise to a further channels here. Stages: inception stage, propagation stage. Those 2 stages. The cavity or a small tube is formed at high stress region, large enough to support PD, but may not be discerned. This is what I said, the initial stage, things that takes place in the micro void or the void which is very smaller, and the PD that is taking place will not be detected by the detector. In AC, it is characterized by the initiation time, but in DC, it is by the number of pulses. Propagation: once the first branch forms, how from the formation of the first branch and then till it breaks down and the complex form it takes, that would be the second stage, is the propagation stage. This is the types of a tree which is available at the literature: branch type tree, bush type tree, bush branch tree. There are also fibrillar tree type of trees, which is something similar to branch type. There can be more branches, but only difference is that the channel diameter will be much more thinner, much more smaller. So this is the tree that is grown in the lab at different fields. Again, that was actually reflecting the 3 different shades of the tree that was mentioned in the literature. Characterizing: how we can characterize a tree is by the fractal dimension. Fractal dimension, we have several methods in order to find the fractal dimension of the tree. It is primarily talking about or primarily characterizing the volume of the tree branches, or the area of the tree branches, we can call it as. So that is what is a fractal dimension. If for a branch tree, it will be between 1 and 2. For a bush tree, it will be between 2 and 3. So higher the fractal dimension, lesser the rate of radial extension, which means it will be more and more bushy. And from the bushy tree, that easily the branches would not develop that quickly. So higher the fractal dimension, lesser the rate of radial extension, longer the tree to cross the gap. Tree inception can be associated with the electroluminescence. It was observed by the researchers that the tree initiation was only noted by the electroluminescence, not by the partial discharge at that year. So this was once an indication of that the tree first branch or initial branches have started. Partial discharge in tree. Small voids inevitably occur at these things I've mentioned. So since the permittivity of the gas will be much less than the permittivity of the polymer, so field intensification occurs at the end walls. Or in other words, the void get more stress compared to the solid insulation, and hence the partial discharge take place within the void, and this activity is very repeated activity. This gives rise to, this gives a lot of opportunity for the ionization to take place, and upon sufficient energy, the electrons carbonizes the walls and break the walls of the void, and leading to the tree channels, and then finally it leads to the failure. This is the light emission, which I was talking about, the electroluminescence, which arises out of PD also. So we have a 5Q1 pattern with which we'll be able to measure the PD. Along with that, with the camera, we'll also be able to measure the light emission that arises out of the PD. This I've explained, I skip. So that's a little about the trees. Now the electric trees in DC. I thought to take about these 4 parts. First is the electric trees in AC, then DC, and third is at the high frequency, and fourth at the nanocomposites. So electric trees in DC. XLPE has become the insulation for both EHV and HV systems. Which causes definitely the treeing phenomena. This has increasingly become a serious problem because the world has gone to the development of a lot of DC power transmission, and hence the issue of the treeing in DC need to be addressed. So let us see how the tree initiation in DC compared to what has happened in the AC. When a DC voltage of plus 70 volts or even minus 60 volt was applied on the samples for 10 hours, there was no single channel formed. And if further increase in the voltage will cause either catastrophic failure, premature failure, or even flashover might occur. So this is one reason why the researchers have gone for, in order to make the study, we cannot just initiate the tree by increasing the voltage. However, the negative polarity also might help in initiating the tree in some cases. So some researchers have gone for, applying the this impulse voltage of 50 kV, and then initiate the first branch or initial few branches, because you cannot have a control over how the tree will initiate when you apply impulse voltage. So, so the tree initiation, this is the tree initiation there. But however, in the case of AC, it was not so. Even much lower field, we have seen the tree has been initiated. Obviously, the reason could be there. It is a constant injection of electrons. Constant injection, at the same time retrieval takes place. So there at the tip, one thing is the highly divergent field, and second, this heat formulation. All these things actually leads to very quick formation of the tree, first branch of the tree. Whereas here, since it is a DC, no such a thing that takes place, which means at the tip, these phenomena which is not really occurring there, and hence it takes such a long or such a high voltage for the tree to be initiated. Okay, next important thing is the issue of electrophoresis in DC. In AC, the voltage was applied continuously, and hence we will be able to record the tree right from initiation to the breakdown through the camera, and hence we also can record the PD data also completely. However, in the case of DC, because of the electrophoresis, this is not possible. Electrophoresis is nothing but a kind of a slosh in the oil. So whenever we apply the voltage, the oil get sloshed, and this kind of a foam kind of a stuff is being formed. We will not be able to observe the tree progression, tree structure, and hence we may have to just apply it on a regular interval. The silicon oil would slosh intensely in the test cell, so this makes it impossible either to observe the light-colored thin branches of a tree or to take photos. So the experiment is done only at DC voltage applied periodically, and then the tree was observed. So one such result that I'll be presenting it is this is the voltage, DC voltage that is applied. It might appear that it is a pulse, but actually this TD, this TD that is mentioned here is actually for 15 minutes, and in other case it is for 60 minutes. So it is actually, though technically it is a pulse or it is a ramp wave, but however it resembles or it simulates the condition of a DC as it stays there for a longer time. This is the result of the DC tree. This is a morphology. This is immediately after initiation. This means this is after application of the impulse voltage. And after 10 cycles, it is not, after 10 cycles, this is the tree branching. And after 20 cycles, we are able to see it has grown a bit more. 30 cycles, yes, it has grown a little. After 40 cycles, it has grown even bigger or even longer. And after 49 cycles, it has almost reached the ground electrode. At the same time, it was also radially spreading. So one observation that we can make from the DC tree is that they are growing steadily and they are going straight towards the ground electrode. This was not the case all the time in AC. So at the beginning, just after initiation, the tree is usually a single slender branch in light color. So under the action of DC voltage, which is periodically applied, it expands not only along the field direction, but also perpendicular to it, with the length and density of the tree branch gradually increasing. The tree growth, after the tree initiation, the growth rate would then slow down normally in the case of AC. But here in the case of DC, there is a stable growth observed by the researchers. Actually, it is growing at the rate of about 0.2 to 1 micrometer per minute. So which is much lower than that of AC trees under the same voltage level. In fact, if we compare the tree progress, in one report it says 50 kV. Here in this case, the applied voltage was about 50 kV, whereas this situation is more or less similar to the AC voltage at 15 kV. So 50 kV and 15 kV. That is the level of comparison. That is the level of stress with which we compare and then try to understand the treeing progression. So there is a thin branch is one observation. Number two, steady and slow growth is another observation. Yeah, this is actually is what I mentioned. The higher the voltage, the faster the tree grows from the first plot. And the second one, it says the reason for the longer tree length is due to the more cycles of voltage application. In fact, here it was about 49 cycles that was applied here, 49 cycles, and here it is 19 cycles, if I remember correctly. So this increase here that depends on the number of cycles. So there are two observations that we can make. Tree grows due to the higher applied voltage, and also due to the more number of voltage or more number of application of the cycles. DC tree characteristics. How we can characterize the DC tree? In the AC tree, it was mostly carbonized. Partially carbonized or conducting, and partially it is carbonized or it is partly conducting, partly non-conducting. But if we leave it over time, mostly it becomes conducting channel. It becomes completely dark in the photographs. However, it is observed in the case of DC, these channels, till it reaches the ground electrode, they are very thin. In fact, it is light in color from this reflected light that shows that they are very, very thin in its dimension. So there are a lot of conductive carbonized materials exist in the channels of conductive trees and are black. Yeah, the non-conductive tree channels are white because there is a small amount of conducting materials inside. So the trees under DC stress are observed to be non-conducting type. That is another observation in the DC. So as far as the DC is concerned, the tree is like a bush-like structure. I don't, yeah, we can call it as like more of a branch kind of a structure with slender branches, and they are non-conductive because they are very, very white in color. And the trees grow very slowly at the rate of 1 micrometer per minute. This is because of the higher applied voltage. And the tree length mainly depends on the cycle number and the voltage amplitude. So this is about the DC tree. The electrical tree under harmonic high frequency voltages. The transmission of AC power through the underground cable is more prominent, but because of the presence of the converters at the either ends, the HVDC cable or HVDC system, the converter transformer, the cable, they all go through not just DC stress alone, but also along with that there'll be kind of a superimposed harmonics also being present. So this study really helps us to understand the effect of AC voltage and harmonics is present, on the breakdown mechanism of the insulation system. So the harmonic AC with a higher THDs can accelerate. That was the observation. Okay. Once the tree is initiated near the needle tip, its initial growth rate is high because of the presence of the harmonics. But after only local degradation occurs, it forms a thick carbonized black structure. That's why we'll be seeing it. Okay. This picture, you can just see that the first one, A is of 17 kV 50 Hz. That's completely a bushy tree. 17 kV 50 Hz, completely a bushy tree. This is the B one, has a 10 kV 50 Hz. The only difference is the voltage. So when the voltage is reduced here, the frequency is the same, and the voltage is reduced here, it gives kind of a more of a branchy, not maybe bush branch, kind of a bush branch structure it changes to. The only difference is the voltage. The next CDE, all these are stressed at 10 kV at different frequencies. In fact, increasing order. C is at 150, 350, and E is at 550. So they all, when the frequency is higher, they become more branchy, more fibrillar in type. And the last one, the F, the difference between E and F, both are at the same frequency, but E is at 10 kV, F is at 12 kV. That means the only difference is at slightly at higher voltage of the same high frequency, this becomes mostly of a bush branch type of a tree. So that is the effect of high frequency at the same time high voltage. So under AC voltages, which means at 50 hertz, at lower voltages, which means at 10 kV, the tree-like tree is formed. That is figure B. This one, figure B, a tree-like tree is formed. Whereas but higher voltages, that is a bush type electrical tree is formed. That is A. This is at higher voltage because this is at 17 kV and this is at 10 kV. Now the next one, at high frequencies, a fibrillar type of electrical tree is formed. That is C to E. C, D, E. These are all at higher frequencies. It changes to fibrillar type of trees. What could be the reason for this change in the tree formation? At high frequencies, the charge injection extraction process from the needle material is enhanced. If the tree is non-conductive, the charge recombination takes place there. It will be, and the field enhancement at the tip will be low. This reduces the growth of a tree, which means forming a bush type electrical trees. However, if the tree is conductive in nature, the tree tips will be acting like the point electrode, and this will actually accelerate the trees, and hence the tree will grow more to be like a fibrillar type of electrical trees. So that is one important observation here. Tree inception. In fact, I should have spoken this a little earlier there. The tree inception voltage gets reduced with the increase in the applied voltage frequency. During the treeing process, the charge injection and extraction process from the needle to material occurs. When the supply frequency is increased, correspondingly, the charge injection and extraction process get enhanced. And so the injected and the trapped charges will enhance the local electric field at the tip, and which causes the tree branch to incept. So the tree initiation time is high when the frequency is 50 hertz power frequency, and becomes very less and minimum when it is present with 11th harmonic content with the THD of about 40%. Now, this is what at 10 kV, 3rd, 5th, 7th, and 11th order harmonics. The THD of 10% is given by this ABCD, this first to 4 one. That is on the left, the 4 pictures on the left, and the 4 on the right gives the THD of about 40%. The difference is only the THD. But however, we can see because of the harmonics present, there are more fine branches or fibrillar branches have been formed from tree-like trees. The reason could be as the supply frequency is increased, the PD is enhanced and the trees grows faster through a fine filamentary branches, and that forms more of a fibrillar type tree. And it is to be it's to be mentioned that with the voltage wave with the higher harmonic voltages, with a high dV by dt, this enhances the partial discharge activity. This could accelerate the tree growth. that is a little bit about the trees at the harmonic AC with harmonic frequency. Now the last part, treeing in nanocomposites. The tree initiation at the nanocomposites, LDPE alumina, can be observed here. For the first one, it is at around 10 kV. This is unfilled, this one here, this is an unfilled PE, polyethylene, LDPE. This is, the tree initiates at 10 kV. Whereas the tree initiates when the alumina as a filler is mixed with 1 weight percentage concentration. The tree starts at 11 kV. So the inception voltage is increased slightly. When it is 3 weight percentage, then the inception voltage becomes 20 kV. Appreciably increased the tree inception voltage. And when it becomes 5-8 percentage, it suddenly dropped down to 12 kV. Suddenly dropped down to 12 kV. So this tree inception, actually, though it improves significantly from 10 to 11 to 20, when the when the filler concentration is increased from up to 3%, but it drops down to 12 kV when it is increased to 5%. The reason actually could be due to the percolation. What is this percolation? This increase in the filler loading causes increased trap density. Obviously, what takes place is at each filler, the charge gets trapped at the interface. So when the filler loading gets increased, the filler loading gets increased, the charge getting trapped are also getting increased. And if the trap density is sufficiently high, the trap distance becomes small. The distance is actually between the charges that are getting trapped or surrounded by the filler becoming small, and this would enhance the you can see this actually would increase the interaction between the barrier potential and the trap regions. This would enhance the field there, and this the interaction between the barrier potential causes reduction in the critical field that requires for detrapping. There is a critical field at which the charges which got trapped at the filler will get detrapped. So if they get detrapped, what they will do, they will actually try to move forward along the direction of the field, though slow. So this results in the increasing in the charge mobility in the polymer bulk, which leads to a local breakdown. That would be the one which might be taking place at the higher filler loading, and hence not only the tree initiation is quicker, but the breakdown also is very quicker at a higher percentage of fillers. The tree propagation in LDPE and HPE nanocomposites are observed here. It is becoming more of a branchy for an unfilled LDPE. With 1% filled LDPE, we can see a kind of bush branch, and with 3%, it is more of a bushy with small branches, and with 5%, it becomes completely bushy. This could be the physical model. What could be taking place here is the darker line shows the movement of the charges or the route for charges. They come and they get completely accumulated over the fillers. In fact, these light ones are the fillers. They are also fillers, but this one actually has the charges surrounding at the interface between the filler and the polymer. That's what is taking place here. So as the charges moves, they get kind of attracted by the fillers, and takes more time for the tree to reach its opposite electron. Tree growth region. In the unfilled LDPE, the tree branches reach the length of 2.1 mm after 2 hours. This is after tree initiation. Whereas in the nanocomposites, it reaches only less than 1 mm for the same voltage stress, thus prolonging the tree growth. In fact, tree initiation is also reduced, that we have seen. The progression also is arrested. The tree branch length, it is 870 micrometer for this LDPE, which is filled with 1% of nano alumina, and it is reduced as we increase the filler weight percentage. This is another one which shows the PD 5QN patterns. The left one is for the unfilled LDPE. This is after the first one. This is after the tree initiation. This is 16 minutes. After 60 minutes. And this is the third one is 90 minutes and 120 minutes. This is an unfilled epoxy. In the unfilled LDPE, sorry, not epoxy, LDPE. In unfilled LDPE, we could see the partial discharge pulses are more number of pulses, and the magnitude is also high, and the pattern also appeared to be broader. Whereas in the case of a LDPE nanocomposites filled with 3 weight percentage, we could see all have been reduced. The number of pulses have reduced, the magnitude has been reduced, and the density, pulse density or a pulse number also has been reduced. And at 120 minutes, almost it has come down to few pieces, not unlike in the other cases, which is about hundreds of PC. So this is the addition. This is the effect of nanofillers on the partial discharge. So this also appears to have a partial discharge resistance. Yep, this is what I had to share. If there's any question.
Thank you, sir. Thanks a lot for this interesting talk on tree growing on composites and polymers. So we don't have any questions yet. If you have any question, you can raise your hands.
I can see two
We
questions
have
here.
Actually, Balaji's question, I think he has also understood during the talk, but he wanted to ask.
We can still ask. We can still have a discussion.
Hello, sir. This is Munmun. I have a question. Like, sir, for the high frequency thing, you have prepared sample in LDPE or epoxy?
We have not used
the third case you have mentioned. There, you have shown the images of electrical tree. So the sample you prepared in LDPE, or
this is about the high frequency.
yes, sir. It's next slide. The next one. Yes, this case.
Yeah.
This is in epoxy or LD?
Yeah.
Okay. And one more question, sir. You have said that after after 3 volume fraction, percolation happens. Like till 5 volume fraction, if when we use nano composite, I think it is very till 5 volume fraction, it is too early to get percolation. Sir, can you please explain that?
No, but this the same thing also we have observed it even in the case of a thin films. Up to 3 weight percentage, there is a good breakdown strength. But when we cross 3, then it just breakdown occurs very quickly. This is for about almost for all the three, magnesium oxide we have observed, alumina.
Okay. Sir, so you
Do
have
you
gone
think
beyond.
it's... One sec. Munmun, just give me one chance. I have a comment to make on this question that we are discussing. When you say that you're going to higher percentages, you see a simultaneous decrease in properties as well as increase in conduction. And you're attributing that to percolation. I also feel that 5% by weight is kind of low for percolation to kick in. And what I feel is likelier is that you have agglomeration at these higher percentages. Do you do anything to measure the dispersion? Do you have any diagnostic methods to estimate the dispersion that you have at higher percentages especially?
Only the thin films we have observed, we are able to see the dispersion.
How do you see that?
Through the SEM.
Through the SEM. And do you kind of estimate whether the dispersion is okay? Some quantitative analysis? Maybe you can do that.
Yeah, yes.
Because I have a strong feeling from my experience that what you're talking about is likely to be agglomeration, due to agglomeration. So you need to check that probably.
Sure.
Yeah, go ahead, Munmun.
Yes, sir, that's it only. So according to me, the 5 volume fraction is too early to have percolation.
He is saying 5 weight percent, not volume percent.
Yeah, weight percent. And sir, you can have you checked from 3-4 volume fraction whether there it is decreasing or increasing? Like you have after 3 weight percent, you have said 5 weight percent, and beyond between 3 and 5, in like in case of 4 weight percent, there is any variation or not?
Beyond 5?
No, before 5, like after 3, like it is maybe approximately 4 volume fraction, whether in that case it is decreasing or not.
It is decreasing. In one case we have just measured it, it was decreasing.
Okay.
Yeah. But I'm really surprised at times. It is there in thin films also the same. In in the thin film, of course, it was a plain electrode configuration. However, in the research, we also are able to see even with the point plane electrode configuration, something similar takes place. But of course, what Professor Nandini said, we may have to just explore more on this aspect.
Okay. Thank you.
Balaji, want to ask the question?
Yeah. What does the number of DC pulses mean? Are we talking about unipolar square wave pulses? Yeah, number of DC pulses mean those. I'll take the. Yeah,
sir, I had asked that question before you came to that slide, and then I understood it.
Oh, okay, fine.
I have one question. You had mentioned that the partial discharge magnitude has reduced because of inclusion of nanofillers in the base material. Can you explain a bit on that, please?
If I have to talk about the number of pulses, more number of pulses,
or rather the nature of partial discharge due to inclusion of nanofillers, why does it reduce?
See, the partial discharge, the source of partial discharge is none other than the channels and the diameter of the channels, the size of the channels, the length of the channels, and so on. So in the filled samples, when the channels have reduced, and because the branches have been very much arrested because of the trapping of the electrons around the nanofillers, so the number of branches or the length of branches getting reduced. So obviously this would result in the reduction of the partial discharge magnitude, and the pulses, and all this would be reduced, no?
Yes, sir, understandable. If there was no tree initiation, then also it has been reported that partial discharge magnitudes have reduced. So could you comment on that, please?
Even if there is no tree initiation?
Yes, sir. Even without any tree, let's say for a perfectly uniform field, and then for a perfectly uniform field configuration, after the inclusion of nanofillers, we have reduced partial discharge. So could you add something to that? Maybe could you explain why that is possible?
In the uniform field electrode configuration, if there is already a partial discharge without any trees, it might be taking place at any of those asperities or voids present inside. That could be the only possibility I can think of. But again, that could be the only possibility. But if the fillers are present, these tree branches that might originate from those voids or through kind of any asperities inside will face the same trapping when the fillers are present there. So that's what.
Okay, sir. Thank you.
We don't have any more questions, so thanks a lot, sir. Thank you for your talk. We have one announcement before we head it to Dr. Nandini Gupta ma'am, that we have sent you a form regarding to all the participants. We have sent you a form. You have to fill that form regarding the feedback of this 6-day course, and along with your attendance, filling up of that form is necessary for your certificate. So please check on that and do it as soon as possible, because on Monday the certificates will be provided.
Okay, before we go on to that, Kingshuk, just a minute. Thank you, Dr. Elan, for a wonderful talk. It's good having you here.
Pleasure, ma'am.
Okay, Kingshuk, you can go ahead.
Yeah. So try to fill them up as soon as possible, and we will be making the certificates ready on Monday. So do it before that. And thank you all for. So this was the last technical talk of the course. We had 6